These are the solutions to the first set of gravitational fields questions. So question one is a fill in the blanks, and these are really important. You do need to know these terms, so let's have a look at them. So the first one is a description of what we mean by the gravitational field. So it's important we know it's all masses have this field around them, and we represent this with straight lines towards the center. So you might be asked to describe what is meant by a gravitational field, so that's important. And we would normally assume it's radial, well, it is radial, but we can assume that it's uniform over short distances. Little g, you do need to know, so that's the force per unit mass, very important, and the units are force per unit mass, newtons per kilogram. So you may be asked to show that newtons per kilogram is the same as the units of acceleration, which are meters per second squared. And Newton's law of gravitation, really important. So if you miss out the word point and just write two masses, that should be fine, but point masses is even better. It's an attractive force. It's proportional to m1, m2, so proportional to their masses, inversely proportional to the square of the distance between them, inverse square. So very important you are confident with these definitions and ideas. Question two should be quite straightforward. So this would be a very easy question, or the most straightforward question on this topic in the exam. So make sure we write out the formula as always. We're given big G. The two masses are the same. Do watch out for converting tons into kilograms. So that would be a very common mistake. So we're told it's 500,000, but then it's multiplied by 1,000, so it's 500 times 10 to the 6. And then we're divided by a kilometer. Again, make sure you always check the units. In this case, change kilometers into meters. So it's divided by 1,000. And you should get 16.7. You could include the negative sign, but normally we would miss that out if we're working out the force. We're interested in the magnitude of the force. We know it's an attractive force, so we would just, we can miss that negative sign out. Right, question three, perhaps a little bit more tricky because it asks us to work out the weight, and a lot of students would go straight to W equals mg and then maybe get into some difficulty because we don't know what g is. In fact, that's the question part B. But we do need to remember that weight and the gravitational force of attraction are the same thing. They're two names for the same thing. So they could have rephrased this question, which is what is the force of attraction between the person and the asteroid. So we're trying to find F, which is the weight, and we can just put the numbers in. We've got the two masses. Once again, we're given kilometers, so we need to multiply by 1,000, and we get 13.9 newtons. That seems about right. So always write the formula and the units, very important. Then part B asks us to find little g, the acceleration due to gravity or gravitational field strength. So we've got a choice here. Because we know what the weight is in part A, we could just divide the weight by the mass, which would give us the answer. That's probably the simplest way of doing it. If you prefer, then you could use this expression for little g and calculate g in this way, and it should be exactly the same. So in some ways this is useful because we have different ways to get the same answer, but sometimes students find this a bit confusing because there are multiple ways of answering it very often in this topic, that can cause a bit of confusion. And final question for this set, so very similar to the previous one, the other way around basically. So we're on Jupiter, we're told that mass, we've got the radius, and we're at the surface. Okay, so we can find little g. So write out the formula. We're after the big M, so that's the mass of Jupiter, and we can ignore the mass of the person, that's in part B, and we get 25 approximately. And even though you're not expected to know the value of G on all the planets, I think it's useful to have a rough idea of what it might be. So if you get the answer of 24.9, then you should think, yeah, that sounds about right. It's about 2.5 times the value on Earth. And then we're trying to find the weight. Well, we could, if we wanted to, use Newton's law of gravitation and calculate F. But we know if we've got the value of G, we can just multiply that by the mass and we can get the weight directly. So yeah, do make sure you use the correct formula as we progress through this topic. There are lots of variations of Newton's law of gravitation, so it's really important in this case we pick the correct one for little g.